Hello there, this is Miss Nakayama, and today's lesson starts our chapter 10, which is Sequences, Series, and Probability. And we're going to start this lesson 10.1 with Sequences and Summation Notation. And in this lesson, we are going to find particular terms of a sequence. We're going to use the recursion formula, we're going to use factorial notation, and we're going to use summation notation. It's all about patterns in life and patterns in math. So I hope you'll find this an enjoyable chapter. First off, we have the definition of a sequence. We have an infinite sequence. Okay, it's a sequence. It's a function whose domain is the set of positive integers. Okay, each item or each number that you have, each of the function values is referred to as a term. And if you have a sequence, the term is denoted by a subscript. So a sub 1, a sub 2, a sub 3, a sub 4, so forth and so on to a sub n. The domain of any function, as we said earlier, is the set of positive integers. Now, if that domain is fixed, then we have a finite sequence. So an infinite sequence goes on forever and ever. A finite sequence is one that ends. So this is what you got to be able to do. Write the terms of a sequence from a general term. This is a general term. So if you were going to write the terms of that sequence, remember the domain is the set of positive integers. So I'm going to start with 1 to find a sub 1. And whatever term I'm finding in, I'm going to plug that in for n. So 2 times 1 plus 5 is 7. So my first term is 7. A sub 2 is 2 times 2 plus 5, which is 9. A sub 3, 2 times 3 plus 5, which is 11. A sub 4 is 2 times 4 plus 5, which is 13. So the first four terms of my sequence are 7, 9, 11, and 13. Example 2. We have same type of thing. We just have a different sequence given. A sub n equals -1 raised to the n over 2 plus 1, 2n plus 1, 2 to the n plus 1. So anywhere I see n, I'm going to replace it with the term I'm looking for. So a sub 1 is going to be -1 to the first power over 2 to the first power plus 1. And when you simplify that, you get -1/3. A sub 2, anywhere I see n, I'm going to put a 2. So -1 to the 2 and 2 raised to the 2. And that's going to give us 1/5. For my third term, anywhere I see n, I'm going to put a 3. So -1 to the third, 2 to the third plus 1. Parentheses are very, very important if you're using your calculator to do this, okay? So this becomes -1/9, and a to the fourth is going to be -1 to the fourth over 2 to the fourth plus 1, which is going to be 1/17. So my terms are going to be -1/3, 1/5, -1/9, and 1/17. Okay, so that's a general term. We also have something known as a recursion formula, and a recursion formula always defines a term in the sequence as a function of the previous term. So it looks a little bit different. All right, this is example 3 using a recursion formula. And notice, all right, find the first four terms of the sequence in which a sub 1 equals 3. When you're doing or finding or using a recursion formula, they always have to give you the first term. Or if you have to write it, you always have to give the first term. And then a sub n equals 2 times a sub n minus 1 plus 5 for n greater than or equal to 2. So we're starting at 2. We already know what the first term is, but let's go find the second term. And the second term, I'm still doing the same thing, y'all, and that is I'm plugging in 2 whenever I see n. But this time that 2 represents a subscript, so this would really become 2 to the a sub 1 plus 5, which is why it says 2 times the previous term, because a sub 1 comes before a sub 2. So 2 times a sub 1 plus 5. Well, what was a sub 1? a sub 1 is that very first term they gave us, which is 3 in this case, and that becomes 11. So when I go find a sub 3, that's 2 times a to the 3 minus 1 plus 5, which is 2 times a sub 2 plus 5, which is 2 times what was a sub 2? The previous term, which is 11, and that becomes 27. First 4 terms means I need to find one more, a sub 4, 2 times a sub 4 minus 1 plus 5, which is going to be 2 times a sub 3 plus 5, and a sub 3 is 27, and that becomes 59. So my first 4 terms are, I didn't write it. We'll go ahead and write it now. It is 3, 11, 27, and 59. Those are the first 4 terms. Okay. Factorial notation. I think y'all have all seen this before, but just in case, if you ever see n with an exclamation point, it does not mean to yell it. It is read n factorial, and it is the product of all the positive integers from n down to 1. So whatever you have, n, and then you subtract 1, 2, all the way down till you get to 1. And by definition, 0 factorial is equal to 1. You need to remember that. So look at what you got to be able to do. Find the terms of a sequence involving factorials. This is example 4. So in this particular case, a sub n equals 20 over n plus 1 factorial. So my first term, a sub 1, is going to be 20 over n is 1. So 1 plus 1 factorial. Well, that's 20 over 2 factorial, and that's equal to 10. You do have a button on your calculator that will do this for you. If you have any trouble finding it, let me know. Sometimes it's in a probability submenu, so find the probability button. So a sub 2 is going to be 20 over 2 plus 1 factorial, which is 20 over 3 factorial, which is 10 over 3. A sub 3 is going to be 20 over 3 plus 1 factorial. That's 20 over 4 factorial, which becomes 5 over 6. And a sub 4, 20 over 4 plus 1 factorial. 4 plus 1 is 5 factorial, and that becomes 1/6. Again, if you need help using your calculator, you need to come see me. So our terms are going to be 10, 10/3, 5/6, and 1/6. All right, example 5. Sometimes, y'all, your calculator can't handle it. I'm not saying these aren't necessarily examples of it, but sometimes when you're working problems, you'll get an overflow area. So it's important for you to know how to operate with these factorials. So an easy way to simplify them, even without a calculator, is to know that that top is 10 times 9, and then I'm going to stop when I get to 8 because I have 8 factorial on the bottom. And the bottom is going to be 2 times 1 times 8 factorial. Well, I have an 8 factorial on the top and an 8 factorial on the bottom, so it's just 10 times 9 divided by 2, which is 45. Now, if I have it as an expression, n plus 1 factorial is going to be n plus 1 times, if I subtract 1, remember we're subtracting 1 each time. So if I subtract 1 from n plus 1, that's n plus 1 minus 1. Well, the 1's cancel out, leaving me with n factorial, and I'm stopping there because I have an n factorial on the bottom. And that is going to, again, have a common factor on the top and bottom. I can divide out, and so my answer ends up being just n plus 1. So it's kind of important to know how to just simplify them. All right, last thing we got to talk about, summation notation. And summation notation is denoted with the letter, the Greek letter for sigma. That's what that button means. That means add up all the terms. And the one on the bottom, the I, is the index of your summation. And it tells you, and n is the upper limit when 1 is the lower limit. So if you see this, I equals 1 to n, so a sub I means a sub 1 plus a sub 2, 3, 4, all the way to a sub n. Add up that many terms. So look at this example. Expand and evaluate the sum, each sum here. So I have A says the sum from I equal to 1 to 6 of 2I squared. So my function itself is 2I squared. The first term is when I equals 1, and that's going to give me 2. The second term is when I is equal to 2, and that's going to be 8. The third term is when I equals 3, and that will be 18. 18. The next one was I is 4, and that'll be 32. And then I got to keep going all the way up to I 6. So 2 times I is 5, and that's going to be 50. And then 2 times I is 6 squared, which is going to be 72. And then I have to add all of those up, and that gives me 182. So it might be a little more complicated in part B when you have an expression here, but still do each one separately. And notice you don't always have to start at 3. You could start at 0. You can start at any number you want to, but this one only goes from 3 to 5, which means I'm only going to have 3 terms. So my first one is 2 raised to k equal to 3 minus 3. 2 to the third minus 3 is 5. And the next one, k is equal to 4. 2 to the fourth minus 3 is equal to 13. And the last term is 2 to the fifth minus 3, and that is 29. And when you add all those up, you get 47. All right, look at this last one. Don't want to trip you up here. Again, I equal to 1 to 5. So you can count 1, 2. I is going to be 1, 2, 3, 4, 5. I'm going to have 5 terms. And in every term is going to be 4. This is the first one. That's when I is 1. I is 2. I is 3. I is 4. And I is 5. There is no I, so it never changes. It's actually a constant. But I still have 5 terms I have to add up. So my answer is going to be 20. All right, last example. That is going backwards, writing sums in summation notation. So it says 1 cubed plus 2 cubed plus 3 cubed all the way down to 7 cubed. So summation notation means I'm going to have that Greek letter sigma. You can use whatever letter, I or K or whatever, but I'm going to start with I, and it is easiest to start with 1. So I'm going to say I equals to 1, and if I equals 1, I have 7 terms. So I'm going to stop when I gets to 7, and they made it kind of easy. Hopefully y'all can see that the only thing that's changing is the base here, and that's my I, and it's always I cubed. So that's all it is. All right, look at part B. 1 plus 1/3 plus 1/9 plus 1/27 dot 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 1 plus 3 to the n minus 1. Okay, again, I've got a sigma. That's my summation. I'm going to start with I equals 1. And I don't know how many terms there are here. Okay, but I will tell you that if they ever give you something like this, y'all, then that's what you want to use. So that's what I'm going to have as my expression. I equal 3 to the I minus 1. 1 over 3 to the I minus 1. And you can check it. If I is 1, 1 minus 1 is 0. Well, what's 3 to the 0? 3 to the 0 is 1. 3 to the 0 is 1. And 1 over 1 is 1. And that's the first term. So I know that that works for the first one. And if I had I equal to n, the last term I have is n, so that's what's going to be at the top. And that's all you have. So I hope you will practice those and think they're a little bit fun, more like putting pieces of a puzzle together. Thank you so much for watching, and y'all have a great day.